All right, well, thanks for everyone who's coming here, and thanks for the organizers for inviting me. But so my name is Matej Penciak, and I'm going to be talking about Lampe, a tool that we're building at Reilabs. So the title of the talk is Shedding Light on Noir with Lampe, and the idea of Lampe is we're going to be understanding Noir code a little bit better at the end of this talk, hopefully. So the one thing I want to mention is that because this is a workshop, I want this to be a relatively interactive talk. So I'm going to go through my slides, shouldn't take too long, and I want the latter part for maybe the last 20 minutes or so to be like a question and answer, and then also a interactive component. So if you have your laptops and you want to join along, play around with Noir and Lampe, go to this QR code or to this ZK Summit 13 talk Git repo, and then click on the code space, or the big green code button, and then the create code spaces on main button right there, and then that'll get the whole process started. It takes a little bit for the code space to get started because it's a Docker container and it has to download and extract and something. It's not going to be on your local machine, but it'll be somewhere in the cloud. But it still takes a little bit of time for the GitHub runners for this to work. So if you get started now, by the time I get to that part of the talk, everything will be ready. All right, so I want to say this is a talk about formal verification, and I should say up front that formal verification is hard. No one really wants to do it. I mean, we've all been in the place where we worked really hard. We wrote a few hundred lines of code. We implemented a new feature in one of our projects, and then we get to the GitHub PR review process, and one of the reviewers says, "Oh, there's not enough testing." And you're like, "Oh man, I just want to get this merged and move on to the next thing. Fine, I'll write some tests." Maybe they are a bit more of a stickler and they say, okay, well, you've tested all of these unit cases, but you haven't, done any property-based testing. And you're like, oh man, that's really annoying. I now have to start pulling out some property testing libraries. I don't really want to do that. And then it gets even worse. And what if this person's even more of a stickler and they say, okay, where's the fuzzing? Where's all this stuff? So all of these tools, testing, fuzzing, et cetera, are all within the umbrella term of formal methods. And formal verification is just a part of that. And it might be sort of the most heavy-handed part of formal methods. But the idea is that instead of just testing your code, you're going to be writing specifications in some sort of machine language. And I'll be talking about the kind of language we're using for Lampe later. But you're going to be formally specifying the properties of your code, and you're going to have to, actually take the time to write these out. And so this is a long process, and it's generally pretty hard. Even harder is actually sitting down and proving the properties as well. So not only do you have to spend all the time to write down the specifications, you actually have to spend a good amount of time to actually prove this stuff as well. Consider the small 200-line feature that you just implemented. That's going to be a lot of overhead that you're going to have to implement all of this proving. And generally, if you just ask anyone out there, formal verification has a high barrier to entry. So you have to learn new tools. Say I'm implementing a new feature in Noir. I'm going to now have to learn a completely new language in order to do this. Oh, I don't want to do that. I want to keep with my Noir language, maybe Rust. I don't want to learn another language in order to do formal verification. And now I'm going to be using some bespoke tools that maybe someone else on my team has written for this project. I don't know exactly how these things work, and there's maybe 3 or 4 people that I can ask questions from, and they're not going to be very helpful in the end anyway. So the theory and the tools that I'm going to have to learn are prerequisites that I don't really want to spend too much time on. And then finally, there's a lot of repeated work. So a lot of times in the formal verification space, people are going to be writing tools that can work in very specific domains or work on very specific projects, maybe something as specific as a single library, maybe a little bit slightly more general, maybe a set of libraries or a set of domains within a language. And maybe even a particular language, but the amount of repeated work is a little bit of a barrier to entry as well. And so the idea behind Lampe is let's try to make this process of formally verifying a little bit easier. So we're in the course of working on this project, we've brought together some well-established theory. We're not reinventing the wheel. We're taking things that are well-known within the theory literature for formal verification and combining them into a useful product that makes the life of the user a lot easier. We're building tools. So the end result, this Lampe tool that we're building, is user-friendly, doesn't assume you have a PhD in computer science in order to work with the tool. Not saying that a PhD in computer science is a bad thing, but not very many people out there have it. So we don't want to restrict our tool to only people who have a PhD in computer science. We want people, just general Noir programmers, to be using this tool and verifying their libraries. Writing the proofs could be hard, but if there's sufficient automation in there, it could be a lot easier. And so we've written a fair amount of automation to make the proofs easier, so that in the end, you don't have to reason about the exact semantics of the language or the exact specific properties of how this language, how the different language components piece together. We want the proofs to basically mirror the language or the core logic that you're trying to implement with the functions that you're implementing. And so the proofs with this automation should generally be relatively understandable. And I think one of the big components is we want these proofs to be composable. So we want all of the different libraries to be able to talk to each other via not only the libraries written in Noir, but also the proofs that are going to be extracted as well. So once you have these proofs over for this library, we want the proofs to also be applicable to this other library over here. So the proofs in the end should be composable. And I'll get into exactly how we make the proofs composable, but it deals with not specifying too much and not making too many choices for the extracted proofs. And then another big barrier to entry for, which I didn't really mention last time, a big barrier to entry for formal verification is that a lot of times, by the time people get around to formally verifying software stacks, it's been around for a long enough time that the amount of code written in that language is insurmountable. There's no way you can formally verify everything from the very beginning to the very end. But Noir is relatively early in its lifespan, and there's really a chance that if we start early enough that we can end with a whole ecosystem of Noir libraries that are formally verified and that can work together. And as more get, as a larger portion of the language gets formally verified, as a larger portion of the libraries get formally verified, it gets easier to formally verify things later on. So, like I said, Lampe tries to solve this problem for Noir, and I think we've come to a nice kind of place with it, and I think in the end it really does solve this problem. So, quick introduction to Noir for the people who aren't familiar. So, it's a language, it has Rust-like syntax. Actually, let's just show everything. As Rust-like syntax, it compiles to a circuit-type intermediate representation called ACIR. I think it stands for Abstract Circuit Intermediate Representation. It supports a lot of the language features that you're familiar with in Rust, like generics, traits, mutability, references, loops, conditionals, etc. There's a few tricky things. This being a ZK language, you need to know, or the Noir compiler rather, needs to know the length of the loops. So if the loop doesn't have a finite length, the compiler is going to complain. It needs to know vaguely that your function is going to terminate eventually, so it has some sort of rudimentary termination checkers in there. And but otherwise, like, you can program in Noir pretty much exactly how you would program in Rust, and you should be very familiar with all of the general language constructs. And you can see here, this is an example of a Noir code. It should look very familiar to you if you've programmed in Rust. It has these traits, binary hash or trait. It has maybe some types that aren't familiar to you if you come from Rust, like field, but that's not so surprising if you're doing some ZK context type stuff. And then we have a loop here, let mute to define mutable variables. This is all very familiar to us. And then the last feature that makes Noir a ZK language, in addition to compiling to ACIR, is this ability to have unconstrained code. So there's no example of unconstrained code here, but you can write sort of like unsafe blocks in Noir. That's kind of like unsafe blocks in Rust, but instead of circumventing the borrow checker, what it's doing is it's circumventing, it's going to be generating some unconstrained prover hints for the circuit in the end. And so you don't really get to control exactly what the unconstrained hints are saying, but that's where a lot of the power of ZK languages comes from. If you bring in unconstrained things, but then have constraints at the end that actually constrain the stuff. You can get a lot of leeway out of that. So let's introduce, so that's a quick introduction to Noir, quick introduction to Lampe. So it's made out of 3 components. The 3 components are an extractor that turns Noir into Lean. So I'll a little bit more about Lean later, but Lean is the language where all of the semantics and the proofs and stuff are going to be done. And so we have an extractor that turns Noir into Lean. It extracts before monomorphization, so it will keep the generics intact. And this is one of the key components that makes the proofs that we write composable. So you can write proofs about generic Noir programs, and you don't specify to the particular instantiation of the generics. And so if you have a library that's fully generic and a lot of different generic parameters, you can then prove things about that library and specify to all the different domains when you use it in the different domains. The output of the extractor is a human-readable DSL in Lean. So this is important because you want to make sure that the extractor isn't doing anything crazy. Well, I'll show you an example in a bit, but it should mirror very closely to what you've written in Noir. The expectation is you're not going to be writing very much of this DSL, but if you really wanted to, you could. And you can reason about things in the Lean side and then go back to Noir. That's an interesting workflow that might be possible. So the next component of Lampe is implementation of the semantics of Noir in Lean. So I'll say a little bit more about exactly what semantics means in the context of formal verification. But essentially, this is where we can sort of encode what it actually means to write, what this block of Noir code actually means. And this is where we actually start reasoning about things. And then the last component, which is important to make the tool usable and friendly for users, is automation. And so we've introduced a number of tactics that make the proof automation or the proofs a little bit easier, and that they should mirror the code structure that you have in Lampe, or the code structure that you have in Noir, rather than having to dip into complicated things that only computer science PhDs care about. So we shouldn't have to worry about how the semantics is specified. In the end, the proofs should really just mirror how the Noir code is written. So here's an example of an extraction. So on the left-hand side, we have Noir code. This is taken from an example that we've done previously implementing a particular hash function. But on the left, we have Noir code. And in the CLI, or in your command prompt, you just type lamp, and it'll generate some sort of new Lean code. And on the right-hand side, you see the Lean code that's generated. And you'll see that it actually looks very similar to the left-hand side, except for maybe some extra annotations here or there related to types and things that we don't want to have to do on the Lean side, like type checking. So like, for example, you see the RL function, you have u shift left 1, or with the top bit, and over here you see the exact same thing implemented on the right. And then similarly, rotate left, you're just repeating this loop n times, and on the right, you see here again, it's repeating n times. So this is an example of the extractor. So the next component of Lampe is the semantics. So I'll just do a really quick crash course in semantics. How do we reason about computers and computer programs generally? So we encode the logic of how we're going to be proving things about Noir in terms of these things called Hoare triples. This is something that's well known, has been around for a long time, since the 90s, I believe, maybe earlier. But the idea behind a Hoare triple is you have three components, P, C, and Q. So P and Q are predicates, things like propositions, things that you're sort of trying to prove about the Noir code. These can be like invariants, or these can be like just general properties about the state that the Noir code is being executed in. The C in the middle is actually the code that's executed. So when you see a Hoare triple like this, P, C, Q, you want to read this as something like saying, when P is true, P is a predicate. If C is executed, then it will terminate, and Q is true. So we call P the precondition and Q the postcondition, and C just essentially the code that's being executed. And so a Hoare triple is essentially a way that we can encode the semantics of a particular code block for Noir. And the basic rules, there's a lot of rules about Hoare triples, and I'm not going to go into every single one of them, but one of the most important ones is this one right here. And it's written out in a way that is very common, that you'll see in a lot of computer science papers. And I'm introducing it here just so that whenever you see these kinds of things, you don't get too scared. But this is an example of a judgment. And what this judgment is saying, if you sort of parse it out, this, okay, now I'll take this. We have these two we have these two Hoare triples here. And if these two Hoare triples are true, then this last Hoare triple is true. Okay, and so now let's parse out what these three Hoare triples are saying. So this is saying that if I have a precondition P, execute C1, then the postcondition R is true. This one is saying that if I have the precondition R, I execute C2, then the postcondition Q is true. And the end result is something about composition of these two code blocks, which is saying that if I take the precondition P, which is the initial precondition, execute C1, then execute C2, then the postcondition Q is true. So this is kind of like one of the basic building blocks of Hoare triples, and it's one of the ways that you can use Hoare triples to reason about programs, or reason about semantics of programs compositionally. There's a lot more. For example, if I know like P implies Q, then if the postcondition is P, then the postcondition should then, you can replace the postcondition with Q. There's a lot of rules about Hoare triples, and I'm not going to go into all of them, but you know, they all kind of have this similar flavor where you're going to be putting things on top of the judgment line and the conclusion is something on the bottom of the judgment line. And then I should say also, I think I'm happy to take questions at any point. So if you have any questions about this or anything else I've talked to about so far, so just please interrupt. Yes. 1 second, they need to get you a mic. Yeah, no worries.
Is there any assumption that it's all sequential here? It has to be sequential or not?
Yeah. So yeah, I guess we're not doing like distributed systems yet, maybe. We can see. But yeah, so this is an example of sequential composition. So this is crash course in Hoare triples, crash course in separation logic. These, because Noir has mutable state with references and mutable variables and function references and all that kind of stuff, we need to talk about the state as well. So whenever we're dereferencing a function pointer, for example, or we're changing the value of a mutable variable, we need to somehow talk about the state. And instead of encoding the entire state in these preconditions and postconditions, some really smart computer scientists a few years ago, like in the 2000s, I think, came up with this notion of separation logic, where you can sort of separate out your state into these little blocks, and you don't have to specify the entire state at any given time. You can only specify the state that's being talked about at any given point. So we'll see a few examples of this when I get to the interactive component, but yeah, it's roughly saying that, you know, we can talk about the state without having to refer to the entire state at any given time. And for the user, the reason why I'm saying you don't really need to know a PhD in computer science in order to use Lampe is that a lot of this separation logic can be automated away and the user never has to really worry about it. And this comes from this idea of minimal preconditions, in the sense that there's going to be a minimal P here in the sense of like logical implication for which these kinds of judgments hold. And if we just kind of keep track of the minimal precondition at any given stage, we don't have to worry about specifying that at every given stage. We can just kind of compose these things together and really only worry about the initial precondition and the end and the very end precondition, very end postcondition. This isn't literally true. There's going to be states in the middle where you're going to be you know, it's not completely automated away. You have to be a little bit clever sometimes. In particular, whenever you see a loop, you're going to have to be a little bit clever and specify these things called loop invariants. And then whenever you have a function call, sometimes you're going to have to be a little bit clever as well. But other than these like two sort of situations, generally, we would hope that the automation that we've implemented gets rid of any notion of these preconditions. So this is almost good enough. What I just specified on the last slide is almost good enough to talk about Noir. This kind of stuff was implemented for a lot of languages that we're already familiar with, C, C++, maybe not C++, definitely C. I know there's projects in Rust that are trying to use separation logic to reason about Rust code. But what's different about Noir is that we have these unconstrained / unsafe blocks, these prover hints that we don't have in just traditional language contexts. And this is where some new ideas had to get introduced. And so there's a paper by I'm not going to pronounce that right. Is there anyone who's French in the audience who can? No. Okay. I'm going to do my best. Chargurad? So what's that? Khud? Okay. I won't get it right, but thanks. So they have a paper about omnisemantics, and the context of the paper was to reason about non-deterministic computation. So I can't really read the author's minds, but I assume they were thinking things like introducing random variables into functions and all that. But it just so happens that this is the exact right idea to reason about Noir code as well. And so in addition to these Hoare triples and these separation logic type ideas from earlier, these omnisemantic judgments are introduced, and what they essentially imply are statements of the following form. So for all possible values, the following predicates hold. So if we introduce an unconstrained hint, we have no control over what that value is. And so the best that we could hope for in our proofs is that no matter what value you fill into this hole, this following predicate holds. And this is the idea of omnisemantics, and this is how we've implemented the semantics of Noir. So whenever you see an unsafe block, and there's an example in the sandbox, you'll see that it just kind of gets extracted to a very simple, hey, this thing exists, we have no idea what it is. And presumably, if you've written your code carefully enough, you should be able to prove the specifications you want between the unsafe blocks and the extra constraints that you've added in. So here's an example of the semantics from omnisemantics. This is as implemented in the paper. You don't have to read through this. This is just a bunch of fancy rules. And over here, again, a big block of text. You don't have to read this, but this is how we've implemented in Lean. So we have all the different rules, and there's almost like an exact one-to-one correspondence between the rules on the left and the rules on the right. And then now, once we have the semantics and we have the DSL, we can start doing proofs. And so here's an example of a proof that we have about Noir code. So if you recall from a few slides ago, I have this rotate left function here, which I've extracted to this rotate left function here. So this is, again, you basically take a U8 and you rotate left another U8 number of times. And so what I've done in this example proof is I have this rotate left function. This is now Lean code. This is just straight up like a declaration in Lean. I'm repeating this RL function n times. And here's a proof that the extracted Lean code, or the extracted DSL, matches this reference implementation. And so you can see here a little bit of this Hoare triple stuff starting to appear. So we have this n less than 24. This is our precondition for the Hoare triple. We have this function body here. This is essentially saying we call the rotate left function with inputs input and n, okay? And then this is our output Hoare triple, which is essentially saying that the output of the function is equal to, if I call this function ref dot rotate left, input n. So you can sort of see the Hoare triples mirrored in the function in this theorem declaration that I have. And then this by block starts the proof, and this is just a straight up Lean proof. And if you're familiar with Lean, this should look familiar, modulo a few different specific situations related to Noir. But we have a lot of automation here that we're using to make this proof a little bit easier. So we have this enter decal automation. We have the steps automation, which is kind of like the catch-all. This is how you should be stepping through your function. We have this loop inv function, which kind of tells us that this is what should be true about the state at any given point inside the loop. And then we have a little bit of a Lean proof here that we have to work through, which is related to the function logic. So this is more of a complicated example. There's easier examples in the interactive component at the end. So I've kind of told you what Lampe is and what Lampe does, but let's just say a few words about what Lampe doesn't do. So it doesn't verify the implementation of Noir itself. So it's not verifying the compiler. It's not checking anything about the constraints that are generated. And it doesn't automate your job away. So as you saw, we had to write the proof manually. So there is some automation, but it's not going to be doing all of our work. So you have to write your own specifications, and you have to guide Lean through the proofs of correctness. And in the end, it also doesn't execute Noir code yet. So there's a little bit of an idea that we could try to automate some very simple proofs away by just literally saying, oh no, just run this function and you'll see that this is the right result. And so some very simple functions should be automated away in this way. But as of yet, we don't run Noir code exactly. So now just to get you a little bit ready for the interactive component, here's a little bit about Lean. So it's a functional programming language with Haskell-like syntax. So I've shown a couple examples of Lean code already, and if you're familiar with Haskell, it should look familiar from that. The difference with Haskell is that it has a type system that's expressive enough so that it can specify things about propositions about Lean. So it can specify, like, you can do existential quantifiers like the exists backwards E kind of letter. You can do for all upside down A, universal quantifiers in Lean. So you can encode all of this kind of stuff in the Lean type system. And with these, together with the sort of expressiveness of like the calculus of constructions, whatever that is, you can sort of just talk about mathematical objects. You can talk about Lean objects. You can talk about Lean data, and you can start proving things about them. So a question is like maybe why use Lean? There's Lean is not the only interactive theorem prover out there. It's possibly the most user-friendly though. And it was originally written, back in 2011, and there's many iterations. We're already on the Lean 4 version already. And Lean kind of has turned into a tool that's very useful and familiar to mathematicians. And so if it's good enough for mathematicians, it should be good enough for computer scientists or people who just generally talk to computers all day. I was a mathematician in a past life, and I would say I did not know very much about computers when I was a mathematician, and I would say, I think even as the sort of naive mathematician I was back then, I could still use Lean. And so there's a large community of mathematicians building libraries of formalized math in Lean. This is a mathlib. This is a library. If you go Google mathlib or something like that, you'll find it. It has a ton of math that's already formalized. And they've also implemented a ton of tactics or proof automation that make your life easier when you try to write Lean proofs. So we have all of these tactics, and I think actually even in the last couple slides, you saw examples of these tactics. So we have RW, short for rewrite, apply, ring, linearith, simp, ASOP. There's a lot of tactics that have already been written about, or already written in Lean that make your life easier when writing proofs. And then, oh, yes?
Just in general terms about rock.
Yeah, yeah.
Just in general terms about rock, that was formerly known as cock.
Yeah.
How does that compare about like adoption and features?
I would say it may just be my experience, but so in terms of the type theory, they're very similar. So mathematically, I think they're very similar. In terms of the tooling, I would say Lean has very user-friendly tooling. I've recently tried to get Rock, I've worked with Rock, and the Rock tooling is getting a little bit better, and I think they've kind of gotten pushed a little bit further because the Lean tooling is so much better. But I would say the Lean tooling is still a little bit better. In Rock, the automation, the tactics are implemented in OCaml, basically. In Lean, they're implemented in Lean. So this makes it a little bit easier for mathematicians where you don't have to learn a wholly separate language in order to do the metaprogramming. The metaprogramming is entirely in Lean itself. So I would say they're very similar. And even the syntax and the tactics, LTAC looks very similar to the tactics monad in Lean. They're very similar. But I would say the real big difference is this automation. Metaprogramming is a little bit more robust in Lean. It's a little bit more user-friendly. And I think it has a little bit more buy-in from the math community. So I think the general culture in Rock is that people will write libraries which prove certain results and kind of keep those as standalone libraries. The general culture in Lean is you'll write these separate libraries, but the eventual goal is to upload them eventually to Mathlib, this central repository of mathematics. And so it's a little bit more centralized and a little bit easier for you to get started as a mathematician. But that's a good question. Yeah?
So maybe this is a dumb question, but what do we get when we have an ecosystem of Noir libraries that are formally verified that we're not able to do without them. I know we've talked a little bit about like in the auditing context. It kind of touches there, but I'm just curious how you would answer that.
Yeah. So I think I have, no, in a couple slides, but I think the big thing that you can get out of it is, well, here's a really good example. So say you want to implement some very tricky optimization where you might have to use some unsafe code and do some constraints after the fact, and you know it's going to make your Noir code run a lot faster, but you're not 100% sure that this doesn't have any bugs in it, doesn't have any ways to exploit the code. If you can do this Noir implementation and then formally verify that it actually does satisfy the specification that you expected, then you're golden. You don't have to worry about any unexpected bugs, modulo, how the semantics or how the extractor, there's some trust that you have to have. But I think it makes you feel a lot more comfortable about the Noir code that you've written in the end. And if you're, say, like writing a banking app, for example, in Noir, and you want to make sure that if I say I'm sending money to this address, then it actually really does go to that address, you can be a little bit more confident about how the Noir code is going to behave once you have these formal specifications specified and proved in Lampe. Yeah. Any other questions? Okay. Yeah, so metaprogramming tactics in DSLs. Here's a lean example. Actually, we've already seen a lean example. That Lampe stuff that I've written previously is a lean example. But the general user experience when you use lean is you're going to have some lean code that you're writing on the left-hand side, and you're going to have this thing called the info view on the right-hand side, which tells you the tactics. If you're familiar with like these two-column proofs from like high school geometry, or like if you're really advanced, like middle school geometry, you'll see that kind of we're writing down the step-by-step kind of proof over here on the left-hand side, and on the right-hand side we see the state that we're in on the right. It's a little bit different because we have automation, and we didn't have automation in our middle school geometry class, but this is kind of the idea. And so here we're proving things about natural numbers and commutativity of addition. We can even prove things about like lean objects and lean theorems, theorems about lean objects. So here we're saying that if I take two lists and I append them, then the lengths add. So this is an expected property about length and appending, and we actually have a theorem that literally says that this is true in the lean context. So kind of getting to your question, like what this gives us is we can use Lampe in a number of different ways. We can have a reference implementation that we've implemented in lean, and then prove that the extracted Noir code has an equivalence with this reference implementation. So say this reference implementation has some proofs of correctness already about it, then we can now get automatically for free proofs of correctness of our Noir code. We can prove invariance of our Noir code, kind of like this example that I had with the banking app, something that will never happen or something that will always happen given I run this Noir code with a particular precondition. And then the other example I gave, we can prove equivalences of optimized Noir code with unoptimized Noir code and check the correctness. And we don't have to worry about unexpected bugs. And then finally, sort of this is a little bit more of a technical, but it's kind of like a nice idea. You can attach proofs to traits in Noir. So now you have traits that really ensure certain properties about our trait, or proofs that ensure certain properties about our trait. So for example, if you implement like a hash function, you can prove that, well, hash function's a bad example. Say you implement something about a sorted list, or you have the trait about sorted lists. You can enforce correctness of that trait by attaching proofs to it on the Lampe side. The fact that the underlying data is actually always sorted no matter what operations I enact on it. And then finally, kind of just how you should be using this is you should, I think a good idea is that you want to kind of implement implement Lampe in your CI. So if you change your Noir code, the proofs are going to break, but you'll have a chance to fix them, and this might give you a insight into how changing that Noir code might have introduced vulnerabilities that you weren't originally familiar with. Okay, and so I'm just kind of like at the very end where we go from here. There's a lot of bug fixes, developer experience, documentation, et cetera, that we still have to do. But I think the big thing is that Lampe is generic enough that we expect that this should be applicable to many different kinds of ZK languages. So far, it's specific to Noir, but the core logic, the core semantics is very general. It's just separation logic with omnisemantics. Any ZK language which has unsafe blocks should be applicable to that domain. And we're hoping that eventually we'll make it applicable to that domain. Okay, and so yeah, definitely try out Lampe today. Here's the GitHub repo for the Lampe repository. Open issues, play around, have a good time. And then now let's get a little bit into the interactive demo in the last maybe like 10 minutes that I have. So before I do that, does anyone have any questions? Oh. So this probably also happened to you guys. But yeah, so just restart your code space. Yeah?
One minor question. Since Lampe will not touch any ACIR code at all, do you see any possibility of any form of improvement there? Would there be any gain from having integration there at all?
So I think it would be helpful to have, so I think that's a good question. I think what would end up having to happen is you want to have a verified compiler that turns Noir code into so the compiler turns Noir code into ACIR. You would want to have a verified compiler that ensures that these kinds of things, if there's optimizations or something, don't break. That's a big undertaking, and I think there is gain there, but I think from the context of like a Noir developer, like from my perspective, if I'm just going to be writing Noir code, I don't want to worry about the Noir compiler. Maybe it's up to Aztec to worry about that formal verification. But if I'm writing my library and I want other people to use my library, I want them to be able to use my library together with the proofs that I've written to ensure that when they're using my functions, they're acting the way they expect them to. So I think that is definitely something that's worthwhile, but I think the idea of Lampe is that it shouldn't be a tool to verify Noir itself. It should be a tool that Noir users use to verify their own code. Yeah, that's a good question, though. Any other questions? Okay, so yeah, so if you enter into code space, you should see like a little bit of a quick start guide. And a disclaimer at the end that there are bugs and you will run into bugs. But if you do run into the bugs, let us know or open issues on GitHub and we will fix them as fast as we can. But I want to start with this simple example here. I've just kind of written this function out by hand. I said one generally does not write this DSL by hand, but again, it's not too hard. But you see here, I define a mutable function, et cetera, et cetera, et cetera. And then I get into the proof. And so here I've separated out the proof into the 3 component. Oh, is this too small or can people see this? Good? Okay. So I've separated out the statement of this proof into 3 components. I have my precondition here. Which is empty, essentially saying that no matter what environment I'm running in, this should be true. If I call my function, then the output of the function should be equal to the input. This is actually not true. I just wanted to give you an example of like what happens if I try to prove something that's not true. And so I mentioned sort of like the use case or like the feedback loop you have as a Lampe or a lean user is you're going to enter into these tactics blocks and you're going to sort of start giving it declaration, or you're going to start giving it commands and it'll start executing proofs for you. And so here I'm in this tactics block and I'll execute the first command, which is called enter decl. So I'm calling a function here and you'll see that if I enter the declaration, I've now entered into the body of that function. And I have now sort of an unrolled version of what this function is really doing. And the idea behind the steps tactic is it should be kind of stepping through the code one step at a time. So if I replace this with a 1, you'll see I originally had like a let z be something. Now that has turned into something about the state that I'm in. So this is now, this right here is our tactic state or our proof state. And we have our precondition here. We have our postcondition here. The postcondition is the same postcondition that I have in the declaration of the function. And this is the code that we're sort of stepping through. And as I step through this code, one step at a time, you'll see that the tactic just kind of like, starts stepping through. I can do it like 10 times or something like that. or I can just say steps all the way through, and it'll get to the final state, which is presumably, we have all of these hypotheses, and then we're trying to prove the end result, which is that x is equal to the input. And it's definitely not true that it's equal to the input because I've multiplied z by 2 and I've added 5. So the end result should not be equal to the output, but that's, if I do like a short for simplify, okay, now I need to start typing. A simp all, it's not going to work. But if I change the hypothesis from input to 2 times input plus 5, okay, maybe I have to do a subst vars. See, now proofs can get a little hairy sometimes. Okay, it's not going to work. This was a bad example. You may have to be a little bit more tricky with the proof. But the idea, this was really just here to show you that steps should sort of turn, at this point, at the very end of this proof, we're not doing anything about Noir. We're just reasoning about the actual code itself. And I may have actually even written this wrong. But the idea is that we want to, in the very end, just prove some basic thing about lean. A better example, which I have worked out ahead of time, is this Fibonacci example. So we're in ZK. I feel like all the ZK VMs or whatever use Fibonacci as a benchmark. Let's use Fibonacci as a benchmark for how to verify things. So here you see a very natural definition of the Fibonacci function. This is just straight up lean code. Here I do a little bit of a modification to it so that I can take not natural numbers as inputs, but uint32s as inputs. That's just because that's what Noir is expecting. But, and here here's just like a slightly extra lemma that I have to prove. So it's clear that this has the inductive property about Fibonacci, that fib of n plus 2 is fib of n plus 1 plus fib of n. But it's not 100% clear that this is true about here as well. So I have to prove like an extra theorem. So everything above this line is just lean stuff. But this here is, now let's expand this out. This here is a proof that an extracted version of the Fibonacci, oh God, sorry, these are not Vim bindings. Here I have an example of the Fibonacci function extracted. I actually even have the Fibonacci Noir function right here. So here's Fibonacci function defined as a loop. You're just looping through n times, et cetera. Just kind of how you expect to calculate Fibonacci. I've run the Lampe CLI function, and I get the Fibonacci extracted right here. It looks very similar to the original Noir code with the loop kind of right here with the mutable A and B defined at the very beginning. And here I prove that this extracted Fibonacci function here, if I call it on n, should be equal to fib of n, fib of n as you would expect. And the proof is a little longer just because it's more complicated, but it mirrors the same sort of structure as the proof that we were just doing earlier. So you enter the declaration, you have your function body here, you step through it up until a certain point, and steps is going to terminate up until the point where it's like, I don't know what to do next. Here, I don't know what to do next happens to be when I get to this loop. And now I have to specify what's happening in the loop. And what's happening in the loop is that at any given step of the loop, if you recall A is defined to be 0 at the very beginning and B is defined to be 1 at the very beginning, A should be a reference pointing to the value fib pi, and B should be a reference to the value pointing at fib pi plus 1. So I've sort of said, okay, at any given point in the loop, this is what's going to be happening. And now I enter into the theorem about the loop. And now I'm in the loop body here. You can see this is basically just what's happening in the loop body. I do steps, et cetera, et cetera. And then the key, this is all leanisms. If you're familiar with lean, this should look familiar. If you're not, then this is going to be a little bit of a magical incantations. But then, oops. And then at the end here, it kind of boils down to proving that fib of pi plus 1 plus fib of pi is equal to fib of I plus 1, which is kind of what you would expect. And this is all just, again, what you expect. Again, we get to the end, you have to do another steps and substvars, and then refl at the end should close the proof. So this is an example of a fib, and I think a nice benchmark, or a nice example of what this benchmark is showing us is that the size of the proof is what? It's something like 20 lines. So proving that this Fibonacci function has a certain property took about 20 lines, given the length of the function is about 20, right? So 2 to 1 of the length of the proofs to the length of the function declaration. The overhead of writing the proof is there, but it's not unreasonable. And then there's other examples. So here's an example of unconstrained functions. So here I have a new variable that I've defined to be unsafe equal to 3. And then, or another example is I've let y equal to new, where this is an unconstrained function. And if I look at what this extracts to, we are just completely unsure of what the value of this thing is. It's unsafe, so the best that we can say is this is like a fresh value, and this is what it is. Yeah, there's a few other examples. Here's an example of how generics work. So here I've just defined some generics, and I have some properties about the function. So I define trait implementation, et cetera, et cetera. And how this is extracted is I have some, the Noir structure is extracted over here. So I have the generics pair structure. It's extracted with the generics still generic. And then I can specify something. So here's an example of how the proofs can compose with each other. So I had the two functions. Let me actually pull that up again. So I have the two functions that I've defined about pair, or like the two associated functions make and make diag. And this function, these equal, should basically prove that the result of make with AA and make diag should result to true. So in the end, I should hope that this function equals true. And if I go back to my theorems here, I have a small auxiliary lemma about make, saying that if I calculate make, the output will just be sort of like a pair of AB. Here's a theorem that says if I take make diag, the output will be a pair AA. And then this is like a simple theorem that kind of goes into the fact that this is going to always be true. So the output of these equals function should always be true. And you'll see here that the structure of the proof is pretty similar to how we've already done it before. So we have an enter decal. The body of the function is pretty wild. That's because I've set some things to false here. Actually, let's delete that. Then we step through it. We have to enter blocks, call functions, enter blocks, call functions. There's a little bit of a bug that I noticed in preparing this example. So we're peeking behind the curtain here with these applies. This will get fixed. But then in the end, we're trying to prove that essentially this x equals true, given all of these hypotheses. It's a mess, but usually simp all just kind of like works, and it does in this case. And if it doesn't, then we've sort of done something wrong, and we need to make the automation a little bit better. But this kind of gives you an idea of how one can start proving things about Noir code by using our extractor and then just generally writing these kinds of proofs pretty quickly. So that is good. I guess I ended a little bit later, but if anyone has other questions in the last couple minutes, then let me know.
Thank you for the talk. So if I understand it correctly, the extracted part is the automated part, and the specs part is kind of what you use the extracted part, but also you manually define kind of some of the specifications of the program itself.
Yeah.
So yeah, in that case then, the manually defining part kind of naively sounds like, well, writing tests for the programs themselves.
Yeah.
In that case, how do you see the difference being like writing tests for a program versus doing the, I guess, formal verification specification of a program itself?
Yeah, so like I said in the beginning, tests are like testing, formal verification, these all fall under formal methods. And testing is generally like a prerequisite to getting any code merged onto GitHub, right? Like if you're not writing tests, you're not doing it right. So that's like the minimum that you would want to have about your Noir code. Writing a formal specification is a little bit more of an ask, and it's a little bit more, it's a little bit more effort for the user, but it's probably worthwhile for the user to expend that effort, because if this code is going to be used by millions of people and potentially have like large financial consequences for errors in the code, then you would want that to be correct. Then the final step of like actually proving that specification holds for the Noir code that you've extracted is a fair amount of effort, but it could also be relatively worthwhile. Like writing the specification out might get you to think about your Noir code in a more like systematic way, but actually writing the proofs out is gonna give you that peace of mind that you're 100% certain. So, tests, depending on how you write them, unit tests will test like a bunch of different examples. If you do property-based testing, that's gonna maybe find a little bit more bugs. But if you have a fully verified Noir code, then modulo some trust assumptions, you could be 100% certain that it's behaving the way you expect.
Makes sense, that helps. Extending to that a bit, so you also mentioned one of the value props of like targeting Noir is that Noir has a very early ecosystem. So libraries can start, I guess, formal verifying their libraries and grow into kind of a full ecosystem of verified libraries to begin with. How do you see that tie-in being beneficial at an early stage versus like a later stage language, I guess, ecosystem? Can't people just extract things from even a late stage library and simply start formal verifying that at a later stage versus an early stage?
So I think a good analogy is something that happened in Python. Python, just completely typeless, dynamically typed. But at some point they introduced type hints, right? And it was really great. All the new libraries started using type hints. But if you start hooking into old libraries that don't use type hints or that haven't been updated to use type hints, you have kind of like a little bit of an assumption of trust in there that's built in on, hey, these types are not going to be the wrong ones at any given stage. Like this might manifest to you with these, orange squigglies saying type any cannot be type whatever, and you have to like do a lot of stuff with pyrite to like, But this is similar to like TypeScript as well, where if you're hooking into JavaScript code, you're going to have all these stuffs with issues with types, and you don't want to, say I'm writing my library, I don't want to have to go into this other person's library and take all the effort to write the type hints for their library, or in the context of Noir, I don't want to have to go into this person's library and write all of the proofs about their functions. I might not even know how their stuff is implemented. Maybe their forward-facing user API is not something that I'm very familiar with. And unless I'm an expert in how they've implemented their code, I may not even know how to write their proofs. And so it is like a big ask to go back to the very beginning for a well-established language to verify all of the code from the very beginning. But Noir is in this unique position where it's a very early language, and if you start verifying things from the very beginning, and if there's a tool like this that hopefully makes it easier for users, you can get a lot of leeway out of that. And it's going to be a group effort, but it's not going to be an unreasonable amount of work for any individual to do. So it's distributed a little bit better. Yeah, I don't know if you guys were able to get into the code space, but hopefully it worked for you guys. Maybe you can play around, have a good time.
So I have some lower priority questions.
Yeah,
Let's tell me about the market support for this product.
Sure.
Do you see LLMs being an issue about being able to jump in to make semi-automation improvements in the formal verification process?
I think so, yeah. So if you ask mathematicians doing lean things just in general, they are very excited about using LLMs and AI and all that to make their proofs a lot faster. Not make writing their proofs a lot faster. We haven't implemented any like AI tactics or anything. There are examples out there in the math context where if we want to get inspiration, we could maybe see what they're doing and see how they're doing it. I see, you know, like I said, kind of in some of these examples, these proofs should be automated in a way. And we've done some of the automation, but it's just not, you know, you can't quite get all the way there. There's too many like edge cases, and you know, maybe we can do about 70% of it with our automation. Maybe AI can bring it to like 90%. I think there's always going to be like a 10% or maybe a 5% amount of like edge cases that no one, unless you're really knowledgeable about the code base, is going to be able to automate away. But I think, yeah, I think it's not unreasonable to expect that AI tactics should be able to help. And the last thing I'll say is there is all this effort for AI tactics in the math side, and these tactics that they're writing are general purpose enough that because there's this robust lean ecosystem, we can hook right into it. And maybe we don't even have to write our own AI tactics. Maybe those AI tactics that are written for the math context are generally applicable for all contexts, and we could just start calling those kinds of things. Actually, a lot of the tactics you see here are not specific to Noir. They're just general tactics that have been written in MathLib to reason about math code, and just so happens that they're, you know, useful for all contexts that have to do with lean proving.
Well, secondary to that, do you see this as becoming the next stage of a audit process, like a guaranteed requirement that any Noir code must have some form of verification with 100%, you know, space?
Yeah, I don't think there's ever going to like there's no governing body, right? That can like fiat, you know, force everyone to start verifying their code. I think the Noir ecosystem would be better if it did have it, and I think it's kind of like our job to make that easier for people to use, and it's not as much of a heavy lift for them to start doing. But I think, yeah, there's a value add to having Noir code being verified, and I think it's not unreasonable to expect that with a little bit extra effort, people will start doing it.
Thanks.
Cool.
Any other questions?
All right, thanks.